This is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to continue the discussion of reflection and refraction. Last time around, we ended with the expressions for the Fresnel coefficients. And basically, any kind of general wave can be broken down into two parts: perpendicular polarized waves and parallel polarized waves. So that's why we broke down our discussion into these two parts. We have the coefficient of reflection is equal to 1 minus alpha beta over 1 plus alpha beta, and the coefficient of transmission, or perpendicular polarization, is equal to 2 over 1 plus alpha beta. And we introduced this notation: alpha is equal to cosine theta t over cosine theta I, or cosine of the angle of transmission or refraction, if you prefer, all over the cosine of the angle of incidence, and beta is equal to mu1 over mu2 times n2 over n1. Now the n's refer to the indices of refraction, and these refer to the permeabilities. What the Fresnel coefficients tell you is that they relate the electric field of the reflected wave to the electric field of the incident wave. And likewise, corresponding coefficient relates the electric field of the transmitted wave to the electric field of the incident wave. Now, if you look in some optics textbooks, they consider non-magnetic media. So I'm going to go ahead and make this simplifying assumption. Basically, it's just going to, the consequences of that is that the mu's are just going to drop out. So we said mu1 is equal to mu2 is equal to mu naught. So that'll drop out of our expressions. And therefore, the coefficient of reflection written out is n1 cosine theta I minus n2 cosine theta t, all over n1 cosine theta I plus n2 cosine theta t. Coefficient of transmission in this case, 2n1 cosine theta I, all over n1 cosine theta I plus n2 cosine theta t. And once again, the S refers to the German word Senkrecht, try to get that right, which means perpendicular. So once we know what the incident electric field looks like, we know its magnitude and direction, you figure out, if you know what the media are, you know what the angle of incidence is, you can figure out everything you need to know about the reflected wave, you know its magnitude and direction, and likewise for the transmitted electric field. And once you know what the electric fields are like, you can use this relation to determine what the magnetic fields are going to look like. Now, perpendicular polarization refers to the polarization of the electric fields, and that means that the electric field is perpendicular to the plane of incidence. The plane of incidence is defined by the incident wave vector and the normal. So remember, we derived one of these laws that all of those three wave vectors lie in the same plane. Okay? So the electric field is perpendicular to that plane. What does that mean? Well, your magnetic field is going to lie in that plane of incidence as well. And again, once you know what the electric fields look like, you can determine the magnetic fields. We also considered parallel polarization, and we derived these two coefficients. Coefficient of reflection in this case is equal to beta minus alpha over alpha plus beta, and the coefficient of transmission is 2 over alpha plus beta. Now, there is ambiguity in the definition of Fresnel coefficients for parallel polarization because they do not relate the vector fields to each other, they relate the magnitudes. So notice there's no arrow drawn on top of these. It's not a mistake. It's that the the electric field of the reflected wave is equal to the coefficient times the electric field of the incident wave. But magnitudes doesn't tell us any information about what directions they point in. And we have a similar expression for the electric field of the transmitted wave. Now, again, if I make the assumption that we're dealing with non-magnetic media, in other words, mu1 is equal to mu2 is equal to mu naught, all the mu naughts are just going to drop right out, and we'll wind up with two expressions that look very similar in form to the ones for perpendicular polarization. For parallel polarization, our coefficient of reflection is n2 cosine theta I minus n1 cosine theta t, all over n2 cosine theta I plus n1 cosine theta t. Coefficient of transmission in this case is 2n1 cosine theta I, all over n2 cosine theta I plus n1 cosine theta t. Again, theta I represents the angle of incidence, and theta t represents the angle of transmission or refraction, if you prefer. So these expressions are the same if you flip around the n1s and n2s, with the exception in the numerator down here. This is n1 in both of these cases. Okay, So if the Fresnel coefficients just relate the magnitudes to each other, they don't give us any information about the entire vector field, then geez, the problem undetermined. Are we missing out on information here? And a lot of times I think when students read that, the definition of Fresnel coefficients is ambiguous. You might think, well, gee, maybe the problem's undetermined. It's not, because along the way, and this is why I like to go through all the nitty-gritty, all the gory algebraic detail, we derived expressions for the magnetic field of the reflected wave in terms of the incident wave, and the magnetic field of the transmitted wave in terms of the incident wave. And notice the coefficients out front are very similar. Well, in fact, they're identical in the case of reflection. For transmission, we have an additional factor of n2 over n1. So the upshot of this is, because we went through all the nitty-gritty, the gory details, you can see, well, gee, if we do know the incident magnetic field, we know everything about it, that means we can figure out everything about the reflected and the transmitted waves as well, as long as we know what their indices of refraction are. Okay, so even though, Fresnel coefficients are defined this way, they relate the reflected and transmitted electric fields to the incident ones, not about the magnetic field. I can still figure out what the magnetic fields are, and then, work my way back and figure out what the directions of the electric field are. And the reason why this happens is because for parallel polarization, even though the electric field lies in the plane of incidence in this case, as opposed to perpendicular polarization, the magnetic fields are perpendicular to the plane of incidence. In other words, if we assume that this board represents our plane of incidence, we've got our incident wave vector coming in at an oblique angle, and there's, let's see, this demarcates two linear media, one on the left-hand side and two on the right-hand side. We've got our transmitted wave going off to the right, we've got our reflected wave going up at that angle. Perhaps, well, the magnetic field, as we say, was pointing out of the board for the incident wave, okay? So that means there are only two directions of the reflected and transmitted fields, or I should say the magnetic fields due to the reflected and transmitted waves can only point in one of two directions. They're either going to point out to, or they're going to point into the board. However, the electric field is now free to point over a range of values in the plane of incidence. So that's why you can't write this. I mean, it's like saying, well, this vector, say, is pointing at an angle 30 degrees, and let's say we figure out this guy's pointing at an angle of 60 degrees. You can't write that as a nice, simple little vector equation with a scalar coefficient. It's not possible to do that. Okay, so that's what's meant by ambiguous definitions. So to maybe illustrate that concept a little bit more clearly, let's look at some simulations. We'll first consider perpendicular polarization. The incident, reflected, and transmitted wave vectors lie in the plane of incidence. We'll assume in this case that the index of refraction of medium 2 is greater than that of medium 1. If the electric field of the incident wave points out of the screen from this viewpoint, so will the electric field of the transmitted wave, because the coefficient of transmission is always positive. In this case, the coefficient of reflection is negative, so this means the electric field of the reflected wave points in the opposite direction or into the screen from this point of view. Magnetic fields of the incident, reflected, and transmitted waves, however, are not parallel or anti-parallel to each other. They can point in a range of directions, and they lie in the plane of incidence. And which way they point depends on the direction of the wave vector. Let's next consider parallel polarization. Again, we'll assume N2 is greater than N1. The magnetic field is perpendicular to the plane of incidence, and we'll assume that the magnetic field of the incident wave vector points out of the screen from this viewpoint. From the relations between magnetic fields, we see that the magnetic field of the transmitted wave will also point out, and for certain angles, that of the reflected wave will point out too. The Fresnel coefficients give the ratios of the magnitudes of the electric fields of the reflected and transmitted waves to that of the incident wave. However, the reflected Fresnel coefficients do not determine the directions of the transmitted and reflected electric fields. The electric field vectors point in a range of directions, and it's impossible to relate those vectors to each other by a mere scalar coefficient. This is why there is ambiguity in the definition of Fresnel coefficients for parallel polarization. Nevertheless, once the directions of the magnetic fields due to the incident, reflected, and transmitted waves are determined, the directions of the electric fields can be determined as well. We haven't derived the Fresnel coefficients for the special case of normal incidence directly from the boundary conditions, but they can be readily obtained from the Fresnel coefficients for perpendicular and parallel polarization. Starting from the Fresnel coefficients for perpendicular polarization, simply set the angle of incidence equals to 0 degrees. By Snell's law, the angle of transmission or angle of refraction also equals 0 degrees, and we obtain the two expressions here. N1 minus N2 over N1 plus N2 for reflection, and 2N1 over N1 plus N2 for transmission. The transmitted wave is always in phase with the incident wave, and the reflected wave is in phase if N1 is greater than N2, and 180 degrees out of phase if N2 is greater than N1. Here we see the wave vectors, the electric field vectors, and the magnetic field vectors for the case of normal incidence and N2 greater than N1. As always, purple represents the electric field, and green represents the magnetic field. Notice the magnetic field vectors point in the same direction, but the electric field, due to the reflected wave, points in the opposite direction from both the incident and transmitted waves. What if we set angle of incidence and the Fresnel coefficients for parallel polarization to 0 degrees? We'll wind up with the same coefficient of transmission. However, the coefficient of reflection will go to N2 minus N1 all over N1 plus N2. Remember, however, the Fresnel coefficients for parallel polarization do not relate the electric field vectors, they relate magnitudes. This is the source of the discrepancy in signs. Nevertheless, we can relate the reflected and transmitted magnetic field vectors to the incident magnetic field vector and thereby determine the directions of the electric fields. Let's revisit the vector diagram for parallel polarization with N2 greater than N1. Mentally rotate the incident wave vector to normal incidence. The reflected wave vector will point in the opposite direction, and the transmitted wave vector will be in the same direction as the incident one. The magnetic field vectors will point out of the screen. And now the electric field vectors will be as follows. The transmit straight up, the incident wave electric field vector will point straight up, but the reflected electric field vector will point straight down. In other words, we're consistent with the results we obtain for perpendicular polarization. Now that we've looked at the differences in behavior of the electric and magnetic fields for perpendicular polarization and parallel polarization, I'm going to go ahead and derive expressions for the coefficients of reflection and transmission that depend only explicitly on the angle of incidence and the angle of transmission. So in other words, I'm going to eliminate any explicit dependence on N2 over N1. Of course, they still depend on the indices of refraction, just the ends won't appear in the equations. Now, if you want to see more of a conceptual discussion of all the topics that we've discussed in part 1 and in this part 2 of this lecture, go to the BocaPhysics website, and on the simulations page you'll see a link to reflection and refraction, and it's a shorter video, and basically it just go over what the Fresnel coefficients, how they behave, and then a lot more detail about how the electric and magnetic fields behave for certain kinds of situations. So it's certainly worth taking a look at. Okay, so if we want to just write dependence, or show dependence on angle of incidence and angle of transmission, rather than having the ends appear, we need to make use of Snell's law. Snell's law is the index of refraction of medium 1 times sine of the angle of incidence is equal to index of refraction of medium 2 times sine of the angle of transmission. Or I can replace I see N2 or N1 in any of these equations. I'm going to replace that by sine of angle of incidence over sine of angle of transmission. So multiply both, or every term in this expression by cosine theta I times sine theta t. Those denominators here and here will just drop out, and we will be left with and actually a plus down in the denominator. Go ahead and consult a table of trigonometric relations. You'll see this is equal to sine theta t minus theta I in the numerator, and in the denominator sine theta t plus theta I. And I wind up with 2 cosine theta I times sine theta t all over sine of theta t plus theta I. Okay, so those are your reflection coefficients of reflection and transmission for perpendicular polarization, with written only as functions of the angle of incidence and the angle of transmission, with dependence on the indices of refraction removed from it explicitly. I mean, there's still obviously dependence on there, but just the ends don't appear. Just leave it up there for a bit, because I'm going to have to erase all of this to give myself more room for to work out similar expressions for parallel polarization. Okay? Same kind of procedure for the coefficients for parallel polarization. Okay, so basically I've got cosine theta I, sine theta I, times something in parentheses. It's just 1 for now, but I'm just leaving myself space because I'm going to add something in here in a minute. Minus sine theta t, cosine theta t, again, empty parentheses. Cosine theta I, sine theta I in the denominator, parentheses, plus sine theta t, cosine theta t, plus parentheses. So right now, you just assume, well, I'll just multiply it by 1, right? If you do the math here, you'll see you've got cosine theta I, sine theta I, blah, blah, blah. Okay, in order to convert this over to a more useful expression, I'm going to make use of the trigonometric relation that if you take the cosine squared of an angle and add to it the sine squared of the same angle, that's just equal to 1. So I'm going to go ahead and multiply this first term through by cosine theta t squared plus sine theta t squared. I'm just multiplying by 1, okay? Do the same thing down here. Term as well, but instead of doing it in terms of theta t, I'm going to do it in terms of theta I. So we have cosine squared theta I plus sine squared theta I up here, and also in the denominator. So multiply everything out, do the math. So once I multiply everything out, I can factor these apart into 2 different factors. So I have sine theta I cosine theta t minus sine theta t cosine theta I. In the denominator, I have cosine theta I cosine theta t plus sine theta I sine theta t. And on the right-hand side, cosine theta I cosine theta t minus sine theta I sine theta t, times sine theta t, all over sine theta I cosine theta t plus sine theta t cosine theta I. And hopefully I did not mix up any of the indices or subscripts along the way. Anyway, the upshot of this is that you'll wind up with, and really don't have the room here. Okay, so this first term is equal to this first factor in the numerators, sine theta I over minus theta t. In the denominator, this is just equal to cosine theta I minus theta t. Over on the right-hand side, we have cosine theta I plus theta t, and then we have sine theta I plus theta t. So, lo and behold, and yet sine with the same argument as cosine below it, and got these flipped around. So basically, this is just equal to tangent theta I minus theta t all over theta I plus theta t. So that is the expression, and you can go through and do all the intermediate steps if you choose. Now, for the transmission coefficient, let me just leave this up here for just a minute before I erase it. Okay, so go through the same kind of procedure as I did in the previous one to derive the expression for the coefficient of reflection. Okay, so I'm going to have the same denominator as I did for the coefficient of reflection for parallel polarization, but of course, because I had to eliminate these two denominators and multiply everything through by sine theta t and cosine theta I. So it's very messy. And there are your coefficients of reflection and transmission for both perpendicular polarization and for parallel polarization. Now there are two final quantities, actually three, that I want to discuss before we leave reflection and refraction for linear media. And basically I want to derive expressions for reflectances, transmittances, and also we define what is meant by Brewster's angle and also by what is critical angle. So let me just leave this up here for a second more. Now that we've written expressions for the coefficients of reflection and transmission for both perpendicular and parallel polarization, let's turn our attention now to quantities that are known as reflectance and transmittance. Anyway, in an earlier lecture, we discussed calculating the Poynting vector for plane waves. So basically what we're interested in is the amount of power that strikes the interface. So Essentially, we're going to take the dot product of the pointing vector and the normal to the interface. And when we were talking about power, we defined the intensity. Or rather, I should say we came up with an expression for the intensity of a plane wave. And that's it before 1/2 times the index of refraction times the speed of light times the permittivity of free space times the magnitude of the electric field times cosine of the angle. The reason why the cosine's there is because if you notice, we have our incident, reflected, and transmitted waves. They're all at an angle with respect to the normal. So anyway, we said that how do you define the angles? How do you define the angle of incidence? Well, it's the dot product of the wave vector with the normal. Okay, so that's where the cosine theta comes from. Anyway, we're interested in reflectance and transmittance, so those are defined as the ratio as the intensity of the reflected wave to the intensity of the incident wave. And the transmittance is defined as the ratio of the transmitted wave, or the intensity of the transmitted wave to the intensity of the incident wave. Well, the reflected wave propagates through medium 1, and so has index of refraction m1. And the intensity of the incident wave is equal to 1/2 n1. Again, it's propagating through the same medium, times the epsilon naught ei naught squared cosine theta I. So all of these quantities out front, all these factors out front, cancel each other out. Now, it's the one of the laws of geometric optics that the angle of reflection is equal to the angle of incidence. So therefore, those factors cancel out. And we're left with the ratio of ER naught to EI naught. Well, what is that equal to? Well, that's just the Fresnel coefficient squared. And this expression holds for whether you're talking about parallel polarized waves or perpendicular polarized waves. Now, looking at the transmittance, again, ratio of the intensity of the transmitted wave to the intensity of the incident wave. So transmitted wave propagates through medium 2, so has an index of refraction n2. So those don't cancel out. The halves cancel, the c and the epsilon cancel out. Also notice that the cosine theta t and cosine theta I also don't cancel out. And so we're left with the transmittance is equal to the ratio of the index of refraction of medium 2 to medium 1. And then it's cosine theta t, cosine angle of transmission, over cosine angle of incidence times the coefficient of transmission. So you have a couple of additional factors out in front. Now, do be aware that some authors don't call these reflectance and transmittance. They actually call them coefficient of reflection and coefficient of transmission. So unfortunately, not everybody's on the same page here, but just remember that this beast here, the ratios of the intensities of the waves impinging or reflected and incident and transmitted and incident. Okay? I'll just leave that up there for a bit. And an important thing I don't want to neglect to mention that if you take the sum of the reflectance and transmittance, that's equal to 1. And that is essentially a consequence of conservation of energy. The reason being is that when you have a wave impinging on the interface itself is not going to absorb any of the energy. So all your energy that comes in associated with your incident wave, well, you got part of the you got a reflected wave and transmitted wave. So that just has to be equal to 1. Okay? So again, consequence of conservation of energy. Now, the last two topics I want to discuss relate to specific kinds of angles or special angles. Let me erase this. Rather than saying where, I really should say for what angle is the reflectance 0. Or what conditions. Now these expressions, as I have them written on the left-hand side, are especially useful for answering these questions, or this question here. So when is reflectance 0? Well, when is this 0? When is this 0? Well, sine of 0 is equal to 0, so one possibility is that the angle of transmission is equal to the angle of incidence, or angle of refraction if you prefer. But if we look at Snell's law, see that this condition holds if the indices of refraction are equal to each other. So in other words, N2 is equal to N1. Some authors would phrase that as that the indices of refraction are optically the same. Okay, another possibility is if the sum of the two angles is equal to pi over 2, because in that case, this denominator will blow up as the argument approaches pi over 2. So the denominator approaches infinity, well, then the reflection, coefficient of reflection, and consequently the reflectance are going to be 0. So it might be useful to find an expression for what that angle is. So if we substitute, well, on the left-hand side, I'm going to write this as N1 sine theta I. But then on the right-hand side, I want to express that in terms of the angle of incidence. So we decided that we have reflectance 0 when the sum of these two angles is equal to pi over 2, so therefore I can write this as pi over 2 minus theta I. And then by using some of those trigonometric relations, I can write this out in expanded form. That's equal to sine pi over 2. Cosine theta I minus sine theta I cosine pi over 2. Well, cosine pi over 2 is just 0. Sine pi over 2 is just equal to 1. And I notice looking left with an N1 sine theta I on the left-hand side and N2 cosine theta I on the right-hand side. Instead of using the subscript I, I'm going to use the subscript B. And this is sine theta B over cosine theta B. Is equal to the ratio of the indices of refraction N2 over N1. So we're going to call the angle of incidence here theta B, and that is just tangent theta B is equal to N2 over N1. And that is Brewster's law. And notice, we only have such an angle for which the reflectance is 0 in parallel polarization. It doesn't happen for perpendicular polarization. And see, I've written these strictly for non-magnetic media. So for non-magnetic media, you will only see reflectance equal to 0 for parallel polarization. Okay? So we got tangent theta b's in 2 over m1, and theta b, of course, represents Brewster's angle. And at one particular angle, the reflectance is 0 and the transmittance will be 1. Okay. Just leave it up there for a bit more. And since we're interested in where's the reflectance 0, well, we're also interested in where's the transmittance 0. Out, this is going to happen at some point if the index of refraction medium n1 is greater than the index of refraction at medium n2. Now the way I've sketched this out on the right hand side of the board, n2 is larger than n1. Why? Because I've drawn the transmitted wave vector as if it's bent towards the normal. Now we're assuming that n1 is greater, so now maybe that's a little exaggerated. But let's see. N1's greater than N2. Transmitted wave vector will be bent away from the normal. Okay? So if I increase the angle of incidence, well, angle of transmission is likewise going to increase. And at some point, or some angle, theta t, is going to be equal to 90 degrees. So I'm going to replace that subscript I by C to stand for critical angle. And that is equal to N2 over N1. And then from any angle beyond that, we're not going to have any more transmittance. We will have perfect internal reflection. The wave's entirely reflected, and what we see is we have a transmitted wave vector. In that case, we just have a reflected wave vector. Okay? That concludes today's lecture on reflection and refraction. We've hashed out the Fresnel coefficients a little bit more. We've defined what is meant by reflectance and transmittance, and also looked at a couple of special angles, Brewster's angle, the case where reflectance is 0, and the critical angle, where the transmittance is equal to 0. Again, I urge you to check out the simulations page on the BocaPhysics website. I do have a link to a lecture there that's really comprised of simulations and just really the bare minimum of algebra. So all these ideas, topics that we've talked about in parts 1 and part 2 are expressed in more conceptual fashion.